All right, in Chapter 4, we're going to move on and look at integers and integer representation. We're going to look at division and modular arithmetic. We're going to look at some base conversion, and we're also going to look at primes, GCDs, and LCMs. Okay, this will be mostly for the math people, but there'll be lots of applications that are used in computer science for modeling some of these algorithms. We're going to start with integer division, and we're not thinking about really lone division here. We're just basically asking ourselves, does a number divide another number? So if we look at this definition here and this symbol, this vertical line right here, right, A divides B is how it's read. A divides B. If there exists an integer C such that A times C equals B. What you're really saying is that B is some multiple of A because you can find a C that multiplies A up to B. So we would say A divides B if, in fact, B is a multiple of A. So we're basically here talking about dividing evenly. So for example, 4 divides 28 because 4 times 7 is 28. The 7 would be the C that connects 4 to 28. Right? 28 is a multiple of 4. 4 times 7 gives you 28. On the other hand, 4 does not divide 30 because 30 is not a multiple of 4, not 30. Right? So the multiples of 4 that are near 30, you would have 28, you would have 32, right? 30 would be somewhere in between here, okay? So since 4 doesn't evenly divide 30, we'd say that 4 does not, with a line through it, divide 30. Now, we're not going to spend a lot of time using this notation. There are certain properties and theorems we could prove, and the book goes into some of those, but those aren't going to really be important this semester. We do touch a lot of different topics on different levels here. We're mostly going to focus on the modular arithmetic, which requires use of the division algorithm. Now, the division algorithm down here is not actually an algorithm, but it sort of gives us the structure of how division would work. Essentially, if we wanted to divide an integer a by an integer d, right, we know that d would go into a some integer number of times with the remainder. Right? And we usually call the answer to the division, d would be the divisor. The answer would be the quotient. And the r would be the remainder. Right? The basic idea is any number a, when divided by a positive divisor d, right, d goes into a q times plus a remainder of r. Okay? So 17 goes into 230. Right? The question is, how many times does 17 go into 230? Well, we can get our calculator out. And we could say 230 divided by 17 equals 13.5 something or other, right? All we really care about is that 230 equals 17 times 13. That's the whole number divisor here, the 13. And if we do 13 times 17, right, that'll give us 221. Right? So we would have to add another 9 to get up to 230. Okay? We could always do long division, make our division house, but we can also use a calculator to do this when the answer isn't obvious. And maybe for a small number, like a number like 40 divided by 3, we could say, well, 40 is really 3 times 13, which is 39 plus 1. The key is understanding that this is the remainder, right? And what we have over here, this is the divisor. Now, they just happen to both be 13 here, but that's not a pattern you should expect to repeat. Okay? Now, we can get into modular arithmetic. We do have operators that exist in math, but also in most computer science languages. We have, when you divide by an integer, you won't get back a decimal. You'll get back an integer. Right? But the question is, do you want the divisor, the quotient, or do you want the remainder? So you can divide a number a by d two different ways. You can divide it to get the quotient, or you could divide it to get the remainder. In a lot of programming languages, if you divide an integer by an integer, it always returns an integer. So if you tried to divide actually 3 by 2, it would just give you the answer 1. It wouldn't give you 1.5 because it has to return an integer. In a lot of programming languages also, the mod operator is used as the percent sign. Okay? So 23 div 17 is 13. Right? We just figured that out down here. Right? 17 times 13, here's your divisor. And 23 mod 17 is 9. That's the remainder. Okay? So we're going to spend a lot of time using the modulus operator, and the modulus operator has a lot of applications that we'll see throughout this chapter. So let's look at the first example here, 13 mod 4. 13 mod 4. Well, 4 goes into 13 3 times, right, with a remainder of 1. So that means that 13 mod 4 is 1. Now if I did 13 div 4, right, that would be the 3 here that I got as the divisor. Now something like 16 mod 4, what happens if I divide 16 by 4? What's my remainder? Well, 4 divides evenly into 16, so my remainder would be 0. Okay? Now if we go back to the definition, I didn't pay too much attention to this detail. The remainder, right, always has to be between 0 and d. It actually should be strictly less than d, because if you can't have a remainder of 5 if you divide by 5. Now let's look at 4 mod 13. How many times does 13 go into 4? Well, it goes in 0 times, right? 0 here with a remainder of 4. And you can expect that to happen anytime the divisor is bigger than the number you're dividing here, right? It's going to go in 0 times and the number will just be the remainder. Okay? Negative 13 mod 4. This is where it gets a little bit complicated. The divisor, as stated over here, has to always be positive. Okay? So you can't say, it might be tempting to say 4 times negative 3 is negative 12, and then just you could subtract another 1 to get to negative 13. But the problem is, this would be, if this was our remainder, it would not be positive. So we can't actually do that. What we have to do is try to go beyond negative 13. Right? So we would actually say 4 times negative 4 is negative 16. Right? Negative 16 on a number line, just think about it. Right? If negative 13 is over here, negative 16 will be over here. And then you can go back this way up 3 to get there. Okay? So when you do the modulus operator with negative numbers, it gets a little bit more complicated. You always have to go one more than the number itself, actually go below it, right? Or think of it as an absolute value and go beyond it. And then you'll have to come up with the remainder from that value. All of these here are small numbers that you could probably do in your head pretty easily. But a number like this, you're going to have to get your calculator out for. Okay? So we get our calculator out. We say 1367 divided by 7 equals 195. So we'd say that 1367 equals 7 times 195 plus some remainder. And the way we're going to get that remainder is to do 7 times 195. That equals 1365. And it should be clear to see that the remainder would be 2 in order to get back to 1367. Okay? So this is something you need to practice. I'm hoping that these first few examples will get, come pretty quickly with some time and some practice and making sure you understand why you have to go beyond the negative. That shouldn't be too complicated. And then the larger numbers, you're going to have to just get your calculator out.